sigma.
T to the 4th.
No, there's something before that. Area, surface area is sigma A T to the 4 minus T naught raised to 4. That's the whole formula. Let me explain. E is emissivity, and what is the emissivity of a perfectly black object? 1. And for a white polished object is 0. You know that, okay. So let's say in a problem it says perfectly black object, then you should know that it's 1.0. So don't ask me for emissivity. And then T is the temperature of the object, but what's T naught? Is the temperature of the surrounding. So if the temperature of the surrounding is not mentioned in the question, just neglect that. Take it as 0. If T naught is not mentioned, take it as 0 Kelvin. Okay? So just ignore that part. So that's a straight, ready-made formula, but remember, what is A? A stands for what? Surface area. Okay, so if it's a sphere, do you know the formula for surface area of a sphere? So you'll hit a roadblock there. You'll be like, okay, I give you the radius of a sphere, and then you have to calculate the surface area. You'll be like, okay, that's math, that's not physics. Sorry, it is physics. You got to know it. So if,
4 pi r squared.
right? If it's a sphere, A is 4 pi r squared. So if you know that, and then sigma will be given. It is Stephan's constant, 5.67 times 10 to the negative 8, watt meter raised to minus 2, Kelvin raised to minus 4. And as an example, if you take, if you're given the temperature of the object as 50 degrees Celsius, can you work it out for me, please? Make matters easier, let's say the radius is given as 0.1 meter. So that will give you this as 4 pi times 0.1 squared, which is going to be, so you get, do you get 0.12568, something like that? So we got the area. Now remember, temperature's got to be in what? Kelvin. So 273 plus 50. How much is that? Is that 323? By any chance? No? So if the problem says, at what rate? That means the time is 1 second. At what rate? Or if the problem says, what power? See? See that? So at what rate means what's the heat radiated in 1 second? Or what is the power exactly means in 1 second? So you got to be careful about that. And then all you got to do is just plug it into the formula and calculate. We assumed it's a black body. Put the value of sigma. Area is right there. And then you have 323 raised to 4. Can I have an answer, please? That's good. 77.56? Oh, both of you got 5.6. And the unit would be? I'll be impressed. Yeah. That's how you do it. So let's go to change in entropy. Change in entropy. Did we do change in entropy? Yes, we did. All right, so suppose you have 500 grams of water at 20 degrees Celsius, and you want to change it to ice at 0 degrees Celsius. And remember, I'm trying to do not the same problem as on the final exam, but giving you the idea, making sure that if you memorize this, you're not going to get it on the final exam. But if you understand what's going on, you're going to get it. So how do we do change in entropy here? First of all, when you read this question, you understand there are two processes involved. What are the two processes? You have 500 grams of water at 20 degrees Celsius. You want to make it ice at 0. But water will not become ice until you lower the temperature to 0. So the first process is water has to cool from 20 to 0. That's the first process. So we have to find the change in entropy for that process, then find the change in entropy when that water at 0 turns into ice at 0. And then add both. You get the total change in entropy. Is the plan clear? Okay, so let's do that. So there are two formulas involved. So for the first case, case 1, water at 20 degrees Celsius cools to 0 degrees Celsius. What is the formula for change in entropy?
Q equals F
That's the formula for change in entropy.
Oh, Q over T, the average temperature.
Q over the average temperature. Yes. And Q is MCAT, like we say it, isn't it? Mm-hmm. So by the average temperature. Okay? So that is, what's the mass? 0.5, because it has got to be in kilograms. The specific heat of water will be given 4,185 joule per kilogram Kelvin times the change in temperature. It's always final, takeaway, initial. Huh? And the final is 0, so it's going to be 0 minus 20 divided by, what's the average temperature? Got to be careful there. The average of 20 and 0 is 10 for sure, but that 10 is in Celsius. The average temperature is 10. Got it? 20 and 0. We've got to change into Celsius, into Kelvin, I mean, so that'll be what, 283 Kelvin?
Yeah.
Okay, and then do the math on that. So I'm getting actually negative, shouldn't it be? 147.88 joule per Kelvin. Yeah, because this is in remember, difference is the same in Celsius and Kelvin. So you get joule per Kelvin. Case 2. Now you're looking at water at 0 degrees Celsius changes into ice at 0 degrees Celsius. And the formula for change in entropy in this case is, again, Q by T average. But Q is what?
M times L.
Could be plus or minus. Why? Because if you're removing heat, it's going to be minus. If you're adding heat, it's going to be plus. Tell me. To change water into ice, are you adding heat or removing heat?
Removing.
So you got to put a minus. Minus. The mass is, of course, 0.5 kilogram. And the latent heat of fusion of ice will be given 3.34, 33. What are you used to? times 10 to the 5 joule per kilogram divided by the average temperature is, the temperature didn't change. It's water at 0 became ice at 0, so the temperature is 0. You cannot put it in Celsius, so it's 273 Kelvin. So I got negative 611.72 joule per Kelvin. So to find the total change in entropy, you actually got to add these two numbers, and that will be the final answer. So the total change what did you get? Negative 759.6 joule per Kelvin. Well, the black lines show the edge of the table, as you would have made, and then you have the red one is a string, like the fishing rope that I gave you yesterday. It's a string. One end of the string is attached rigidly to a point A, and at the other end, well, the string is passing over a pulley, and at the other end there is a mass. First of all, can you give me the tension in the string? Give me the formula for tension in the string, somebody, quick. Tension. Have you heard of tension? Tension is a force. How do you calculate force due to m kilograms?
M times A.
M times?
Acceleration.
What is the acceleration in this case? Gravity. So it's mg, isn't it? So the tension in this case, let's call it F sub t, is mg, which is, I just said, let's say 2 kilograms. M is 2. So 2 times 9.8 will give you 19.6 newtons. That's the tension. If you just pluck in the middle of the string, pluck in the middle and let it go, wouldn't you see waves on the string? This is exactly the setup of a guitar, if you know what I mean. Except that in the case of a guitar, you don't have a weight hanging. Instead, you tighten it, right? So this is a stretch the string under tension, and waves go through it. And the frequency of the waves produced, so if I draw the waves, I really don't want to destroy the diagram, but I'm helpless, I have to draw it. So if I draw the wave setup, it could be something like that. Well, I'm drawing freehand, so it's not perfect. And the waves should all have the same wavelength. So what I've drawn is not exact, you know what I mean. These segments should all look the same. That's much better. Do you see that? So how many segments can you see here? The string is actually showing up as 1, 2, 3, 4, 5, 6 segments. Do you see the 6 segments? All right. So the formula for frequency in this case is F is equal to N by 2 times the length square root Ft by mu. I'm going to explain the terms. N is the number of segments. In this case, N is equal to 6. Ft we already got is the tension. It's 19.6 newtons. The length of the string is the length of the string. I mean, what else can I say? It's just the total length of the string. Let's take the length of the string as 2 meters. Mu is a very important term. That's where confusion happens. Mu is the mass of the string divided by its length. That means you're going to get the mass of 1 meter. Mass of 1 meter of the string. So there are 2 masses here. Please be careful. I'm going to say the mass of the string. You know, how much should be the mass of a string? Would it be like 10 kilograms? No way. Could be a few grams, right? So let's take it as 10 grams. That's a heavy string. So can you find mu for me? Mass of the string is 10 grams, but you have to have it in kilograms. So 10 by 1,000, which is 0.01 kilograms. The length of the string is 2 meters. So what do you get for that? Of course, you get 0.005 kilogram per meter. So we got all of the terms. And now also put F sub n here in the formula, F sub n, to show that that's the frequency when there are 6 loops or 6 segments. So now all you got to do is just plug it into the formula. So 6 by 2 times 2, square root ft is 19.6 by mu is 0.005. And the answer is B. You got 93.9. Who knows the unit of frequency? Hertz. So this is the frequency if the string vibrates as 6 segments, isn't it? So here's another question. What if you make the string vibrate as one segment? One segment. What would the frequency be? Just divide by 6. And that is called the fundamental frequency. So write down, fundamental frequency means the lowest frequency. So fundamental frequency is the lowest frequency. And in this case, the fundamental frequency would be 93.9 divided by 6. And you know why? Because in place of n, where you actually put 6, you would put 1. See? See that? So you would get this answer divided by 6. So how much is that? 15 point something? 15.65 hertz is the fundamental frequency. What would be the next frequency? Times 2, isn't it? That'll be like if there are 2 segments. What would be the next one? Times 3. Those are called the harmonics. So when you see the word harmonic, you know it's multiples of the fundamental frequency. So first harmonic is the fundamental. Second harmonic is 2 times. Third harmonic is 3 times, and so on. For the sake of like putting this on the video, I'm just going to go through it very fast. You know that the total change in heat for both of them added up should be equal to 0. Isn't that how we do it? Yeah. So I just wrote, oh, the H got canceled out. It became like eat. I'm not hungry. It's actually heat change in copper plus heat change in water is equal to 0. And you know it's MCAT for both in this case. There's no phase change in this case. Be careful. So MCAT copper plus MCAT water is equal to 0. And this is going fast because my students actually did it. They're so good. All right, so 0.2 times that, mass times physical heat times change in temperature. Whenever you take the change in temperature, it's final minus initial, isn't it? Don't forget. Okay, so that's for copper, and then for water is equal to 0. Do the math. Well, I can speed it up a little bit more. And if you really need to slow it down, you know what to do on YouTube. So you do that, do all the math, collect the TF terms, get the number, take it to the other side. Don't try to write as fast as I can, because only I can do that. And you get the final temperature as 24.04 Celsius. This one is about buoyant force, Archimedes principle. You know that buoyant force, what's the formula for buoyant force? Buoyant force.
The density of the fluid.
No, actually, the buoyant force is what? It's the weight of the fluid displaced. Remember it that way. Buoyant force is always weight of the fluid displaced. I mean, when you put a solid into any fluid, wouldn't it displace the fluid? Okay. So weight of the fluid displaced is buoyant force. Now we know that weight is mass times gravity and mass is volume times density. Maybe I said that too fast. So finally you get volume of the fluid displaced times density of the fluid times G. Buoyant force is always how much volume of the fluid is displaced multiplied by the density of the fluid times G. That's how you calculate the buoyant force. So now give me the numbers that you got yesterday in the lab. Like, what was the mass of the aluminum cylinder? Mass of the aluminum.
105.6 grams.
So 105.6 grams. And we'll keep in grams. No, wait, we'll change into kilograms. Divide by 1,000, that will be 0.1056 kilograms. And what was the mass of this cylinder in water?
67.3 grams.
67.3?
Yes.
Thank you, ma'am. 67.3 gram, which is 0.0673 kilogram. And we will stop with that, and I want to ask you several questions based on that. Now, from these two masses, can you find the buoyant force? The actual buoyant force. So this is not exactly what you were asked to do in the lab. In the lab you had ready-made formulas you would substitute. But I'm asking you, can somebody tell me what is the buoyant force in this case? Say that again.
You subtract the two numbers.
If you subtract the two numbers, what would the unit be?
Oh, you subtract the two numbers and then multiply it by 9.
Correct? You subtract the two numbers, multiply it with 9.8. Because if you subtract the two numbers, you only get the mass, isn't it? You get the difference in mass. Come on. You want the difference in weight. Is anybody with me? You want the difference in weight. So to get the buoyant force, in this case, you would be 0.1056 kilogram minus, keep that number ready so we save time. How much is that? So we get 0.0383 kilogram. That is not the buoyant force, that's the loss of mass, apparent loss of mass. Remember, mass never changes, right? But this is what it appears to have lost. But you got to multiply it with what? With 9.8. If you multiply mass with 9.8, you're going to get force. So when you do that, you get 0.375 newtons. Isn't the number small? Yeah, because the aluminum cylinder was small. Translate this to a ship in the ocean. That's a huge object, so it's going to go down by a lot, and then the buoyant force is going to be much more, all right? This is small. Did that make sense? Yes or no? All right, from that, can you find the volume of fluid displaced? Use that to find the volume of fluid displaced. Go ahead. Come on. Don't we know that the buoyant force is volume of the fluid times density of the fluid times G? Do we know that? And what fluid did we use yesterday? Water. Do we know the density of water? 1 is in what unit? That gram per centimeter cube, but we need it in kilogram per meter cube, so it would be 1,000. Okay. So you can find the volume of the fluid displaced by that, you have 0.375 divided by density of water times 9.8, and you get, did you get something like 3.827
Yes.
times 10 to the, is it negative 6?
I got negative.
5. Negative 5, yeah, I was seeing it. Negative 5 meter cube. And again, because it's in meter cube, that's why it's like really small. You know, we used a very small aluminum cylinder. So I want to ask you one more last question based on this. Now, in yesterday's lab, didn't you have the whole cylinder underwater? So could we say that the volume of water displaced is exactly equal to the volume of the cylinder? So instead of asking you to find the volume of fluid displaced, I could have gone directly to what's the volume of the aluminum cylinder? See where I'm getting to? So be ready for that. So write that down. So in this case, not every case, if the whole thing is gone under any fluid, then their volumes are equal. So in this case, volume of that aluminum cylinder is exactly the same. Oh, I had an idea. Last, can you now find the density of aluminum? So you're not using the ready-made formulas anymore. Can you find it? Do you know the mass of the aluminum cylinder? Do you know its volume? Okay. If you know its mass and its volume, you should be able to find its density. Okay. So density of aluminum is the mass of aluminum divided by its volume. The mass of aluminum in kilograms is 0.1056, and its volume we just found out, 3.827 times 10 to the negative 5 meter cube. And what do you get? I'm really interested in knowing that. Wow. I got 2759.7 kilogram per meter cube. Am I right? Did you get 2759.7 kilogram per meter cube? Does this compare correctly with the answer we got yesterday? So here's the next question. What is the specific gravity of aluminum? Go, find that. You know, specific gravity is also called relative density, isn't it? Okay, so how do you find it? Specific gravity of aluminum. What's the definition for specific gravity? It's the density of aluminum divided by the density of water. So density of aluminum divided by the density of water. Do you know the density of water? Yes. So if you divide this, by 1,000, again in kilograms per meter cube, the units are going to cancel out and you're going to get 2.759 or 2.76. That's it. That is the specific gravity of aluminum. I hope you understood. Did you? So in this one, you have two masses, 3 kilogram and 1 kilogram, attached to the ends of a string passing over a smooth frictionless pulley. And can you find the acceleration of the system and the tension in the string? Two things. You've got to find the acceleration of the system and the tension in the string. Last chance to understand this. This is where the free body diagram comes in. Do you know what free body diagram is? No? You take each mass and show the forces acting on it. So help me. What are the forces acting on M1? What are the two forces acting on M1? Quick. The gravitational force, which always acts down. Yep, correct. And the tension, which in this case acts straight up. Okay. Which one of these two forces is bigger? What direction is this mass moving in? Downwards, so the force down, mg, must be bigger. Isn't the force down 3 times 9.8? Is that 29.4? I think so. Newton. And tension, we have no idea. But we do know that the downward force is bigger. Are you all with me?
Yes.
And so we apply Newton's second law. What's Newton's second law? Net force is equal to mass times acceleration. So the net force is, we go with the bigger force minus the smaller. That's one way of doing it, Is equal to mass, which is 3 times the acceleration. So we are stuck. We have two unknown quantities. Isn't it? But we know that if we get one of them, we'll get the other one. That's why we'll go to the second object. Look at the second object now, M2. Let's draw the free body diagram for that. Now for that one again, there is the weight and there is the tension, but the difference is going to be which is bigger. Therefore, when you take the net force for the second object, okay, let me label it first. This is 1 times 9.8, which is 9.8 Newton. And the tension is, of course, the same, Ft. But this time, because we know it's going up, we go Ft minus 9.8 is the net force, is equal to 1 times A. So you have two simultaneous equations which you have to solve. Here is the first one, here is the second one. You got to solve them. Now, there are many methods of solving it, but in this case, I think you directly have 1A is this. So what I'll do is, I'll just go 29.4 minus Ft is 3 times, substitute Ft minus 9.8. See what I did? Did you see what I did? From the second one, I got A as Ft minus 9.8, didn't I?
Oh, because A is more.
Yeah, 1A means A. So I just put that value there and I got rid of A, and then I have to do the algebra to get Ft. Would you do it for me, please? To save time, 29.4 minus F sub t is 3 sub Ft minus, again we get 29.4 on this side. Do we? Okay, collect the Ft terms on one side, you will get 4 F sub t. Because I took the negative F sub Ft to the other side, that's 4, and then that would make it 29.4 plus 29.4. Be careful with the algebra. Which is what? How much is that? 58.8? So 4 Ft is 58.8. So Ft is 58.8 divided by 4, which is what? 14.7, is it? Somebody?
Yes, 14.7.
Thank you so much. So once you get F sub t, just put it into this, any one of the formulas, and find A. So A is Ft minus 9.8, which, but we got Ft as 14.7, and that is 4.9 meter per second. That's how you do it. Okay, while I'm building this problem up, I'm going to be giving you so many important points. Number one, the center of gravity of an object is a fixed point. the center of gravity. So if this is a meter stick, well, it's 100 centimeters long. It has a center of gravity. Let's assume that the center of gravity is at 51 centimeter. So the weight of this meter stick is acting through that point. That's the center of gravity. I just assumed it to be at 51. Agreed? And let us say that this is supported at, that looks like 20 centimeters, so it's supported at 20. And I want you to find out what mass, this is such a simple thing, what mass you must put at 10 centimeter in order to balance it. Can you do it or not? Such an easy thing, isn't it? What mass should you put at that? If I give you the mass of the meter stick, wouldn't that be easy? No? Mass of meter stick. Take it as 100 grams. So this shouldn't even be a question, something like this on the exam. I think I should change it. So can you find the unknown mass? Mistake, what you did. You got to just look at the clockwise torque, clockwise torque. Here is what students make, the mistake that they make. Are you all watching? You take the distance. You take the distances. Don't go with the numbers. Students would go with the numbers. I don't know why. You take the distance. So, using the same units, the clockwise is going to be 100 gram times, what's the distance? 31 centimeter is equal to m, of course in grams, times 10. Isn't that 10? So when you do that, you are going to get 310 gram. Don't miss. Did you realize where instead of the distance, did you take the number? That's what I've seen them do. I've seen everybody do stuff now. Like all the mistakes. Okay, so the next question in this context is, can you find the normal reaction at the pivot? What is the normal reaction at the pivot? Normal reaction. At the support or the pivot. How do you find it? There are two conditions for static equilibrium. Who knows the two conditions? We already used one. The net torque must be 0. If the net torque is 0, then there's no rotation, isn't it? But we also need to make sure that there is no translatory motion. So the net force must also be 0. So there are two conditions for static equilibrium. What are they? The net force is 0 and the net torque is 0. All right, what do you mean by net force? Let's show the forces. We are missing one force. Aren't we missing this force? That's what you were asked to find. So if we call it the normal force, it's very easy now. The normal force should be equal to, help me out. What are the downward forces? Plus 310 plus 100. But remember, that's in grams. So if you actually need it in newtons, you know what to do? What do you do? Huh? What? How do you get it in newtons? Really? That's in grams.
Oh, change it to kilograms first.
Okay. And then multiplied with 9.8. And you would get it in newtons. How much do we get? 4.018 is what I have. What do you have? Is that the answer? Yes. Bernoulli's principle. Here is where I went. I said, Bernoulli's principle is based on conservation of energy. See? So if you situate it on concepts, you're not going to forget conservation of energy. And then you go with, okay, Bernoulli's principle. You already know potential energy, do you? Potential energy. What's the formula for potential energy?
MGH.
Yep. So you'll go, okay, potential energy, because when a fluid is flowing, it could have potential energy. Like it may be coming down a tube like that. Something like that, fluid coming down to a tube like that. And you know that from the ground, they are situated at different heights. We call this H1, H2. So that's why there could be a change in potential energy as it comes from point A to point B. But the fluid is also having kinetic energy. Isn't it moving? Okay, what's the formula for kinetic energy?
1/2 mv squared.
Yep, very good. So it has a velocity there, which is v1. It has a velocity with which it comes out, which is v2. That's what we're talking about. So a flowing fluid has both potential and kinetic energy, but it also has a third type of energy. And this third type is only for fluids. Solids don't have that. Can anybody remember what that third type of energy is?
Pressure.
Pressure energy. Very good. So pressure energy, what's the formula? In thermodynamics, work done. What is work done?
Oh, force over area.
That is generally in mechanics, that's correct. But in thermodynamics, thinking of a cylinder with a piston and a gas, what's the work done in compressing the gas? You should immediately come to pressure times volume. Work done is pressure times change in volume, like PDV. Do you remember that? Work done is pressure times change in volume. So here's the deal. We have a problem here. The first two energies are written in terms of mass. The third one is written in terms of volume. Do you all see that? So since we don't like that, we're going to say, hey, let's divide each one by the mass. So you go mgh by m. This is going to be mv squared by 2m. The half is there. And this is going to be, you're trying to standardize them. Divided, and that gives us new formulas. This becomes GH, as you can see, and this becomes V squared by 2. What does this become? Anybody? Look at it carefully. What is volume by mass? Okay, what is mass by volume? So volume by mass would be 1 by density. See? It's reversed. Upside down. So you would write this as, wrong pen. So that would be P by rho. Please don't cancel them out. They're not the same. Write carefully. P by rho. So in Bernoulli's principle, now finally, the sum of these three is a constant. That's what you mean by Bernoulli's principle. Total energy is conserved. So right there you have Bernoulli's principle. And you would be able to work out problems if you also remember that this is another segment, volume of fluid coming out per second. Volume of fluid coming out per second. Do you remember the formula? Area times velocity. volume of fluid coming out per second is area times velocity. Very important. So if you could figure out one of the velocities, look at me. Either V1 or V2, and you multiply it with the area at that point. So let's say you get V1, you need to multiply it with that area. See? You would be able to find the flow rate. And flow rate is very important for you. We're talking about blood flowing through the arteries. Come on. So fluids is important for you. So that's both things coming in. Try to work out some problems and you'll be good. Without giving numbers, just giving you the ideas, there are two vectors which you need to add. Let's say this is 5 units, this is 4 units. And you got to add. How do we add vectors? There is the graphical method, but we always use the component method. Do you remember that? You break the vector into the horizontal and vertical. Can you do that for me? Come on. Let's go. First, for the red one, 5 units. The x component and the y. That would depend on the angle. So if this is 30, do you know that this is 5 cosine 30? I'm reminding you. Are your memories coming back? 5 cosine 30? And this would be what? 5 sine 30. Okay, that's what we do. And then do the same thing for the other one, the green one. So you go break that into this. And that looks like a small angle, so let's call it 10 degrees. In which case, this would be 4 cosine 10, 4 sine 10. And then you would add the x components and the y, isn't it? And wouldn't you get a right angle triangle when you do that? If you add the x and the y? Do you see the right angle triangle? Don't? Okay, I'll make you see it. Can I put that red one here? Yes. Can I shift the what's the best way to do it? Okay, I have the green already there, I have the red there. All right, should try it in green now. I moved the green down, do you see what I did? So in other words, isn't this 4 cosine 10? Come on. Huh? And this is 5 sine 30. Well, if you don't understand, you get like muddled up, mixed up. But do you see what I did? I just moved it, wrote it again. And so you should be able to see the triangle now. Yes or no? Do you see it? So let's have the numbers. Go with each number, tell me the numbers. So those are the values that you get, and if you add these two, 2.5, you get 3.195. And if you add these two, you get 4.33 plus 3.94, which is 8.27. All right, what's the last step? Once you get the x, total x and total y, you know what to do. You find the resultant r by, come on. Huh? Yeah. Just square each, add them, get your answer. At 8.87 units when you do that, and you may be asked to calculate this angle. Let's call it phi. What do you find that angle? Huh? Tan phi is 3.195 divided by 8.27. So when you divide it, you get 0.3604 maybe, and then take the tan inverse of that. Do you have it? What do you get?
21.12.
21.12. Okay, let's. Huh? I got 19.81. Who's doing it wrong? 19.82?
How about 19.82?
You hit some wrong key somewhere. $80. Did you put it correctly, like 0.3604? Are you taking tan inverse or did you hit cosine or something?
Tan inverse, yeah.
Why is it so much different?
My decimal, when I did the dividing first, I got
Oh my goodness, I made a mistake here. This was 0.3, 0. What? 3863. And when you take the inverse of that, Haiti, what do you get?
21.4.
Okay. So that is the end of the review for summer 2022. Thank you.